Okay, so today's Ask an Expert session is hosted by myself and Susannah Martin, whose voice you just heard. She is a senior engineer in the customer training group for Intel FPGAs, FPGA high-level tools, as well as system on chip related content. Prior to becoming a trainer, she worked as an FPGA design engineer, an embedded programmer, and field applications engineer. Well, myself, my name is Riri. I am an application engineer with the technical training team, same team as Susannah, and I focus on high-level design and general FPGA specialization. Prior to joining the team, I worked in the industrial market segments, focusing on development of AI solutions targeting our Intel FPGAs. Okay, that said, this is the agenda for today's session. We start with a short presentation by Susannah. She'll walk us through some of the info about using oneAPI with FPGAs. Then we'll head over to DevCloud for a demonstration, which she's going to also be presenting to us. And then afterwards, we'll have an open forum for any questions that you would be having. And that will come later on. We'll have about 20-30 minutes for that. So with that said, I will be handing off to Susannah to kick off the presentation.
Okay. Hi, everybody. Give me just 1 second to share my screen. Okay. And now let me put this in presentation mode. Okay, and if you come up with any questions while I'm talking, feel free to put them in the chat window. I'm not going to monitor the chat while I'm presenting, but we'll get to that section of questions, and I'd love to have some of yours that are queued up live waiting for me. Okay, so during this presentation, I'm going to go through just what is oneAPI really quickly in the context of FPGAs, and then I will talk about how to get started using it, and then I'll show you the DevCloud. Okay, so what is oneAPI in the context of FPGAs? So first, the why of why we have oneAPI. Basically, we've discovered that heterogeneous computing is great for all of our algorithms. So currently trending, we're happy that we're able to use all kinds of different devices now in our systems, along with the CPU as a host. So we can plug in GPUs nowadays, FPGAs, AI accelerators, all kinds of things are proliferating out there. And we can take advantage of the strengths of each of these architectures. And this, what the strengths are really depends on the constraints of your system. So you might be constrained by power, so performance per watt might be important to you. Raw throughput and raw latency are very often important when we're trying to accelerate our algorithms. I/O flexibility, so one of the strengths of the FPGA is that it can process data straight after it comes through the Ethernet. So that's what we mean by that, something that doesn't burden the CPU with data processing. Memory bandwidth, et cetera. So it just really depends on the constraints of your system, what in particular is important to you. Okay, but even though heterogeneous computing is great, it has had its challenges. So all of these different architectures have traditionally required different programming models, different programming languages, and different tool chains. So there's a lot of learning that had to go on. And if you wanted to target something like an FPGA, you really had to have a specialist, right, that could write RTL to get whatever algorithm that you wanted going. So even though it was great to have these in our systems, it could be difficult. And all of that, came into play with the software development, and a normal software engineer wasn't always capable of targeting different things without a bunch of learning that they hadn't had already. Oh, and let me call out one more thing on the slide before we go on. Sometimes in our literature and our marketing, you will see SV SVMS. This is actually usually you see the matrix over here, so you'll see an acronym called SVMS. In that acronym, what we are really referring to are the different kinds of architecture. So the scalar would be a CPU, the vector would be a GPU. Where the FPGA fits in is spatial. Um, so just in case y'all see that acronym, that's what we mean, just all the different types of devices. Okay, so what we're trying to do with oneAPI is to unify some of this so you don't have to do as much learning to target the different devices. So oneAPI, it's called One because we want one model for all of the different devices. So we want a common developer experience across all of the different devices. So we want to give you a tool chain that will work across all of them. Um, and tools for evaluating performance that work across all of them. Ideally, we want libraries that work across all of them. So we're just trying to unify it and make it easier. So what we do have already is a common language that can work across all of them, and that's called DPC++. And we'll get into that a little bit deeper as I talk. So DPC++ is going to work for a CPU, a GPU, an FPGA. You will need to tweak it to get optimum performance out of all of them. So it just will be a common language. It won't be you write the program a single time and it runs, as performantly. If you first write it for a GPU, you'd want to tweak it before you then run it on an FPGA. But it's all going to be within that language. So once you learn the language, you have the learning that you need to really get started with all of the different devices. And we have based our languages and our tool set upon open specifications, and we've made our stuff open to try to keep that cooperation going and try to also get this proliferated throughout the industry. So you don't necessarily just see Intel stuff that's targeted with SYCL is what it's built upon. So there's different compilers that also take SYCL. Okay, this slide is showing you, so oneAPI is a large offering across Intel and it keeps getting bigger and bigger. So you'll see diagrams like this that try to depict everything that oneAPI as like a family of software products has to offer. FPGAs don't, the stuff that we have targeting FPGAs, it doesn't encompass everything in these pictures. So this attempts to tell you what exactly we have for FPGA. So it's the language, so data parallel C++, and the analysis and debug tools. And the major one here is vTune will now support FPGAs. Okay. The programming language itself, so data parallel C++, is based upon SYCL. It basically is SYCL plus some of our extensions that we have added to it. And we have not added extensions to it to just live as proprietary Intel things. We're just moving faster than the SYCL standard is. We want to give you, everything we can think of to make our devices perform in the best way. So as we think of extensions that would be useful, we go ahead and add them to data parallel C++, and we go work with Kronos to get them added eventually to the SYCL specification. But we're moving faster than the SYCL specification is. So if you know SYCL, you pretty much know all of data parallel C++ except for some extensions that we have added to it. And then SYCL is based upon C++. So if you know C++, then SYCL will be pretty easy to you. It will just feel like an extra API beyond C++ itself. And if you know OpenCL too, the concept, SYCL is kind of an evolution of OpenCL. So all of the programming model for OpenCL was incorporated into SYCL, and Kronos did OpenCL, and they also did SYCL. So if you know any of those things, if you know SYCL, if you know OpenCL, or if you know C++, then this stuff will come pretty easy once you start learning it. Okay, today when you use oneAPI with FPGAs, it's not you're not programming for a raw FPGA. You're actually programming for targeting a board. That's because you're going to have a host in your system, and then the FPGA will be communicating with that host. So that requires a board plugged into the motherboard of that host. And the board itself needs to have something called a BSP, which stands for Board Support Package, and that's so that the FPGA will have the smarts to communicate back with the host through the PCIe, and to communicate with the DDR that's on the board, that you'll be targeting with your DPC++ code. So all of those smarts are built into the BSP, plus some software too for the host. There's a middle layer of software that's part of the BSP. So bottom line, it requires a certain system topology and a board that comes along with the BSP. So Intel has two Intel branded boards that support oneAPI. One is our Intel Programmable Acceleration Card that has an ARIA 10 on it, and one is the next kind of uprev of the programmable acceleration card, the PAC 5005, and that has a Stratix 10 on it. And both of these are installed in the Dev Cloud. So when you start working with the Dev Cloud and you're ready to actually run on an FPGA, these are sitting there in some of the nodes for you to run your compiled code on. And there's some other third-party boards. So if you know FPGAs well, you notice that we're missing our latest family, Agilex, with this offering. There is a third party, so TerraASIC offers an Agilex board, and Bitware offers some boards, and there might be some that I'm missing, but there's other third-party boards that support oneAPI also. Okay, so how do you get started? Okay, so first you'll want to learn a little bit about the language, so DPC++. There are two really good ways to go out there and learn DPC++. The first one is a collection of Jupyter notebooks. If you haven't worked with Jupyter notebooks, then they're actually, you're kind of in for a treat. They're really cool. They're very easy to use, and what they're about is they incorporate both the write-up about what you're learning and the code that you're executing. So as you're reading about it, then you'll have a section of the notebook that's actually executable, and the compiler, all of the commands will be issued to the host behind the scenes. A little engine's actually running the notebook, so it's a way to get your hands dirty as you're, reading about it at the same time. So they're really nice. We have 8 notebooks currently that talk about data parallel C++, and these get added to fairly often. And the way that you get these is when you sign up for DevCloud, when your account is provisioned, they go ahead and place a copy of all of these notebooks into your account. So they're just sitting there waiting for you after you've signed up for DevCloud. And all of this is free. Okay. If you like books better, and also if you want to learn everything there is to know about data parallel C++, we have a free ebook available. I guess I should stop saying we, because this is actually not an Intel thing. There were some Intel people that participated as authors, and we kind of prompt them to make sure it stays up to date. But this book is available at springer.com, and a PDF and EPUB format, or Amazon.com for Kindle, and it is free and it's electronic format. If you want a hard copy, it costs, I think, $40, but most people go ebooks nowadays anyway, so the ebooks are free. Okay, so first learn some stuff about the language. You don't have to know DPC++ real comprehensively. If you work through those notebooks, you'll know plenty to move on and start learning about using FPGAs with oneAPI. And the special parts of using FPGAs mostly come in within the kernel scope. So you don't have to know a ton about the host side of the language before you can start working with FPGAs. And once you are ready to dive in, we have 2 really good pieces of documentation. So the Intel oneAPI programming guide has a chapter devoted to FPGAs, and it tells you how to use the compilation flow that we would like you to use, and the optimization guide goes through every technique that you can use to optimize with FPGAs. And these are not, let me go on to the next resource. Um, what I recommend for people when they are getting up to speed with FPGAs is to go through the optimization guide hand in hand with a full range of tutorials that we have that are at the GitHub, and they're also installed with the base toolkit. And I will show you this GitHub when I go to the demo portion. So when you click into these folders, there's just a ton of tutorials, and it goes, there's one for basically every optimization technique that you can use. And these have write-ups in them too. So every tutorial will have a write-up that you can read about what it's actually showing you. Okay. And then we also have a 4-hour workshop. And so if you come to this workshop, knowing nothing but a little bit of C++, so you will need to know at least that. And this workshop will go through a little bit of DPC++, enough to know what you're looking at when you look at some example programs, and then a little bit of kernel scope optimization with FPGAs, so enough to really get your hands dirty and equip you to keep learning as you go along in your learning journey. And so this is a free 4-hour workshop. We have some coming up in March, and you'll get a thank you email for attending today, and in that email will have a registration link. Oh, and you don't have to have attended today to come to this. So if you want to forward it to your friends once you get the link, that's fine. Okay, and when you're ready to start programming, I definitely recommend the easiest way is to just go to the DevCloud, sign up, and program away. And there are FPGAs for you to use there. The base toolkit's installed on every single node. The FPGA add-on is installed on some of the nodes, and there's GPUs if you want to work with them. So we like to, it's like a playground basically for all of our hardware that you can use with oneAPI. Okay, and if you'd like to install it on your own, you can also do that. So you can download the tools for free to take advantage of, well, to compile all the way to where you have an accelerated function that's running on an FPGA board. You'll need both the Intel oneAPI base toolkit and one of the Intel FPGA add-ons for the base toolkit. And the reason it's an add-on is just because it's a pretty big download. It actually includes Cordis within that download, so they didn't want to make this extra big. So just you download this piece, and you'll have all the pieces that you need. No licenses are required, even though this does have Cordis within it. We don't require a license to run it for the purposes of oneAPI. And remember that when you're ready to run on a board, and you go, buy a board if you're setting up something on your own, that you'll want to buy one that has a supported BSP. Okay, and now I'm going to stop living in PowerPoint right now and show y'all a demonstration. Okay, my start bar has not been behaving well today. Okay, there we go. Okay, so I have kind of cheated and I already have DevCloud up, but let me show y'all how to sign up if y'all when y'all get ready. So whenever I want to find the DevCloud instance, I just search for oneAPI, DevCloud in Google, and the link that comes up is that very first link that you'll need. And when you click on that, if you haven't already signed up for an account, the button here will be prompting you to sign up for an account. And it's a really simple form. It basically just asks you your name, your company. If you don't have a company, it's fine to say self, and what you're doing. Are you researching? Are you a student? Are you trying to figure out stuff for work? That kind of thing. But it's a very short form you fill out, and then you can immediately start using the DevCloud. Okay, so So once you signed up, you go to getting started. And what I clicked to get to what I'm about to show you is down here. So I just launched Jupyter Lab when I'm doing work on the Dev Cloud because Jupyter Lab pretty much has everything I need in it. It includes a terminal. You also can log in to the Dev Cloud using SSH if you want to log in and have a GUI that you can then launch tools that are GUI based. But I usually just work within the terminal. So Jupyter Lab is a very easy way to have a terminal and to be able to run the Jupyter notebooks. So once I click this, it has to start Jupyter Lab, and occasionally you have to wait. So that's why I already have it running, so I don't have to wait. And occasionally all the nodes will be really busy, and you'll have to wait a little bit. So I went ahead and started it, so we'd have it not have to possibly incur wait. So anyway, when you get here, this is the first notebook that will open up. It just gives you an introduction to Dev Cloud, how to run these notebooks down here, and also how to queue up jobs on the Dev Cloud. So just a welcome to Dev Cloud itself. And the other notebooks for DPC++ will also be populated. My account, it's been here a long time, so I have a lot of folders, but you'll just have a few folders, and each folder will be one of those notebooks for DPC++. Okay, so now let me show you getting to a terminal. So within this environment, you can run notebooks. This is an example of a notebook. I'll show you an example of another notebook in just a minute. But you can also do a few other things. So what I do very, very often is just go ahead and pop open a terminal. And then I get a terminal prompt. And this is just like sitting at a prompt on a Linux machine. You'll be able to run different Linux commands here. So anything that you'd like to do. I've set up a little folder for today. And one of the things that I want to show you, and let me also, when you want to pop open a notebook, this is how you do it. So that's what I'm navigating to over here. Okay. And what I wanted to show you before we pop open another notebook is this oneAPI CLI. And this is where all of those examples live. They also live on our GitHub, but this is an easy way to get to it if you're already within a terminal. So oneAPI includes not just data parallel C++, but it also includes a Python compiler and a Fortran compiler. FPGAs are not supported for those, but that's why you're getting choices. So our FPGA examples are all data parallel C++. So I'll click C++. And then scroll down a little bit, and you see all of these different examples for FPGAs. And if I click on one of these, so let's just click on fast recompile and create, and then that will be populated within here for me. So if I go into fast recompile, I see, that it has populated with the examples. It runs with a CMake build flow. If I go into the source directory here, I can actually see that I have a few source files right here. So let's look at the kernel. Okay, so, and you can, look at all the other source. And so that's one way to see all of the source. And okay, for some reason, my bar for Teams is up there. Okay, that went away. Yeah, the things aren't minimizing like they should today. All of those examples are also on our GitHub. So if you would like to, if you prefer browsing the GitHub for them instead, it's all the same examples that I just showed you. And in this view, we can also see this kind of breadth of offering that we have of all of those different examples. So let's click into this one, and we see that each of them has a pretty extensive write-up about what it's actually doing. Some of these have, diagrams within the write-up to really explain fully what's going on. Okay, and one other thing I wanted to show you with our examples is that we have these reference designs. So the tutorials are very simple designs. The reference designs are more performant code. So this is code that is meant to be real world, that has been heavily optimized by our development engineering team. So gzip is just, what it's called. It's an implementation of gzip that actually gives world class performance. And you can take a look at this code and see how we have optimized it. Until you've learned enough, it will be hard to decipher, why we have optimized it. But once you have worked the tutorials and read through a lot of the optimization guide, these are very good examples to look through to see real world optimizations and how we did it. Okay. Okay, so back to the Jupyter Notebook. There's one more thing I want to show you before I open it up for questions. Okay, if you do come to the workshop, this will be one of the notebooks that you work through as a lab during the workshop. So that workshop is 2 hours of lecture, and it's about evenly split, so about 2 hours of lecture and about 2 hours of lab. And one of the things that we uh, really try to hit home with is the development flow when you use FPGAs with oneAPI. And the reason why, if you see this diagram, is it's got the green, the yellow, and the red. We want you to stay out of the red as much as possible. So when you do a full compile all the way down to a bit stream, it's going to take you a long time. It'll take you hours. So we've made sure we've worked many, many years on perfecting this development flow. To where at first you just compile for emulation. So when you're trying to make sure that your code is syntactically correct, and that it's giving you the right answers, we just want you to do a software compile. This compiles into an emulation file that runs on the x86 host, and you can make sure that everything's working like you thought it would work before you move on. And then when you move on, we have a very robust static report that we generate for you so that you can identify most of the bottlenecks within your code. And this is based upon just the early image of the FPGA, which is just the stitched together pieces of IP, which we can generate within minutes, usually like 2 or 3 minutes. And then you can get bottlenecks out. And then finally, you would be ready to compile to bit streams. So that would be hours. But as you iterate through getting out bottlenecks and making things functional, you don't have to wait too long. Okay, and so that's what this notebook talks through. So it has you, it talks through how do I compile for emulation, and then you write out a file here. So the way the notebooks work is I hit play on the cells that are executable. So it just wrote a file, and then I would hit play here. It's running a compilation command. So DPC PP is our compiler command, and then this is telling it I'm compiling for an FPGA. This is telling to compile for emulation, and then my input file and what I want my output file to be named. Okay, when I hit that, it kicks off a compile, and when the star goes away, that means it has finished with that compile. And remember, this is just an emulation compile, so it won't take too long. Okay, so it's done. And then I can actually run it. So I run that emulation file, and it, passed as I expected. And the next part of the notebook walks through doing a compile to generate an optimization report. And then we can take a look at what that report looks like in just a second. And then finally, when you get down to the bottom of the notebook, there's instructions on how to do this walks through a couple of optimization steps too. That's what I just scrolled through. And then it does a full compile here at the end. We definitely will not do that today because it takes hours, but this notebook would walk you through all of that. Okay. And so the optimization report that notebook generated, I didn't actually click that because I'm running. I want to make sure to leave time for questions. But this is the report that would have gotten generated. I pre-generated it. And this is what a report file looks like. So we have a lot of different sections here. Sorry, I'm getting some noise on the line. Yeah. Okay, sorry, let me figure out where this. Okay, when am I good? So in this report, we have different views. So here's the area analysis. This tells me how much of the FPGA I'm taking up in a very fine-grained way. Um, we have loop analysis, which is very important for your overall, what the overall latency of your code will end up being. And if you learn more about optimization, this is one of the first things that you'll learn about. You want to see a one here. So this is an example, a really of a bad piece of code. You never want to see something high, like in the hundreds of cycles. So that's why, and it's a good lab exercise because there's optimizations that you can do here. So this was the first stage, and we were doing pretty badly. Then as you work through the lab, you get better numbers as you make optimizations. Then there's different views. The kernel memory viewer, we have not implemented any memory on the FPGA in this particular design, so this won't show anything useful, but y'all get the idea. There's a lot of different sections of this report. So this is meant to tell you many of the actions that you need to take before you have to sit through, an hours long compile to in order to make the optimizations. This will give you what you need within minutes to start making some optimizations to the code. And it also tells you where in the code. So if I click this, it'll pop me to exactly where it has encountered this this bottleneck here so that you can then correct it. Okay, so there's a lot more to learn. I do encourage you to go to the workshop or read through our documentation and play in the dev cloud and get your hands dirty. But that's how you can sign up for all of that and what documentation to go start looking at. Okay, so with that, I'm going to go ahead and open it up for questions. Let me give you some ground rules for that real fast. Okay. So the ground rules are basically there's not a lot of rules. So the ground rules, any question you can think of is fair game. You can go ahead and talk to me over the voice, and that is great. I love to hear from you, or just type it in the chat. If it is a detailed design specific question, or if it's something that I don't know, I will try to answer it the best I can. And if I don't know, then I'll just let you know that I don't know, and I'll tell you where I think the answer can be obtained. So which documentation I think that answer would be in. And if I don't get to your question, or if I don't have time to answer it as fully as you would like me to, then your local FAE is also a very good reference, or the Intel community forums are a really good place. So that this is the link to those. But with that, let Riri tell you how to ask a question and get to answering questions. Okay, Riri, do you want to tell them how?
Yeah, thank you, Susannah. So, yes, like you mentioned, there are two ways we can ask our questions. First of all, you could unmute yourself and then just ask away, or you could put your questions in the chat window and I will relay to Susannah or answer it myself. So, we already have some questions in the chat window, so I'll just go ahead and read them right now. So, this one's asking how to OpenVINO and oneAPI connect to oneAPI ecosystem.
Okay. So OpenVINO does not, that's actually a different tool chain. And then OPE, okay, yeah, let me just clear my screen and I can bring up things as I need them. And then OPE, okay, so that's a little bit of a loaded question. Currently today, OPE does not factor into oneAPI. Well, that's not true. Okay, currently, OPE factors into some of the BSPs for oneAPI. It depends on which board we're talking about, because OPE was developed after some of the earlier BSPs. But in the modern ones and going forward, OPE is one of the layers of software that helps the host interact with the FPGA. And also going forward, our reference designs for those BSPs, so basically all of them will incorporate OPE, and they will also incorporate reference designs that we will make available, not just for oneAPI, but also doing some other stuff. So we're trying to make that um, reference design that we're basing everything upon as open as possible. And that's ongoing work. And OPE has already become a piece of that. So I'm really excited for the future because this kind of unified reference design model that's going to fit into one API, as well as other kinds of system topologies, is really cool because we'll have that out there and all of our board vendors will be using it. So I hope that answers your question. Let me know if there's any follow-ups there.
Okay, yeah, so same person is also asking if DPC++ is replacing OpenCL.
For new designs, we do see OpenCL. Um, uh, it's waning in popularity. So I um, I can't tell you for sure what the future holds, but I can tell you that as a company, we recommend DPC++ for any
Okay,
designs that you're now starting.
okay. And another follow-up question is asking that I assume there's a shell that is put onto the FPGA and there's the row where the accelerator code goes. Now, is the shell RTL public? Can we change it if we wanted to? I don't know, did you understand the question?
Okay, yeah, I understand that. Okay, so the
Okay,
shell is called a BSP, and that is what we're going to start. That BSP will start being based upon a reference design that we make totally public, that we will want you to look at. Now, having said that, before you step into designing a BSP, know that it's going to take you a while. So if you're an experienced FPGA designer, we expect it to take you 3 to 6 months to design a BSP, even with you starting with our reference designs, because you have to tweak. You have to tweak the design, you have to tweak the software, you have to obtain timing closure, all that kind of traditional FPGA stuff. So if you're not an FPGA designer type person, I wouldn't take on that task. If you are a board vendor, though, that's the kind of thing we want you to take on so that your board can support, you know, as many of our tools as possible. Um, let me get back to the question though. And then today, whether that RTL is public, it really just depends again on which board that you are looking at. I think most of our partners, it still would be clear text RTL, but I'm not sure. They kind of have the decision on their own whether to make that RTL public or not when they release it as a BSP. For our boards, though, so for the pack cards that I showed you, that RTL is public. So if you want to take it and tweak it, then we actually encourage you to do that, and base your own BSP upon that. But just remember, if you start designing a BSP, it's a big undertaking. So don't do it just for just just because you decide that the boards out there aren't quite what you want. Because try to make those boards work if it's just for an individual project.
okay. Yeah, okay. So the other question asked, does the one API for FPGA flow invoke the Intel HLS compiler underneath?
No, it does not. I like this question because you're it's exhibiting a whole lot of knowledge about our tools. Um, it it does not, but they are based upon very, very similar engines. So that's actually another project that we're trying to unify better and going forward. the tool sets are going to become more unified. So we might have less tools than we do today. So it'll be easier to work with both. But today, know that HLS compiler is a separate tool, but know that its mechanics are very, very similar to how we're compiling the oneAPI. So if you know optimization techniques for coding with HLS, and those same optimization techniques are the ones that you're going to be learning for oneAPI kernels. While we're on the topic of HLS, I want to go ahead and address the fact that oneAPI is meant, like I said, for a certain system topology. You're going to need a board that supports, oneAPI. If you want to code with C++, and you just want to target a general FPGA on any board, then HLS would be the tool for that. And HLS will, what it produces for you is it's RTL at the end of the day. So usually it's a piece of IP RTL that people would incorporate into a larger FPGA design. But if you wanted to code it in HLS and have that be your top level, that's also theoretically possible. But HLS does not require a certain topology. It's just for coding. It's a different way of coding instead of RTL. Okay.
Okay. So this question, I think, is just asking how to save reports in PDFs, not in HTML. It says Jupyter Lab can only save in HTML. So, yeah.
Oh, yeah. Let me go back to what I was showing. Okay, so Jupyter Lab. So I looked at this HTML report. The reason it's HTML is because that's what our compiler produces for you for the optimization report. It really doesn't have anything to do with Jupyter Lab, but I did want to kind of show you the magic that happened to make the report possible. So it used to be that the reports themselves, I could just pop them open in Jupyter and it would come up in a different tab because it was HTML. So, theoretically, this is a browser and, it should come up. Well, Chrome and every browser, they increased their security and now it won't come up within Jupyter. So you have to, when you have a report, let me go to where that cell that actually does it. So all of this stuff that it looks is in a gray block like this, it's all executable. And what these codes executing is just writing a file. But what these other blocks are executing are calls to the system. So down here is the call where when I ran this command here, the compile, this was to generate a report file. So after this runs, there's a HTML report file sitting in, it's actually pretty deep. Let me see. I think it's in bin. Yeah, so it creates a project directory for you when it runs, and then the reports are in a subdirectory of that. So this is the report that it generated. With this command, the system call down here, I reached into that directory, I zipped it up, and then I just copied it up to the directory where we were sitting when we launched this Jupyter notebook. So right up, oh, did I go too far? No, I didn't. Okay, so right up here. So I zipped it and then I deposited it right here. And then you can right click and download it. So then I had it locally. So I unzipped it and I just popped it open for you here. But it doesn't have anything to do with Jupyter Lab. It's just how our compiler produces that report. It's an HTML report, so you can pop it open in your browser. And unfortunately, it has to be local. Now it can't just open in Jupyter Lab.
Yeah. So I think he corrected himself and said he's actually asking, okay, so this is how the question came in. I already have a DevCloud account in Jupyter Lab and I can only save in HTML but not in PDF. Basic toolkits only have FPGA using OpenCL, but I cannot find more samples using DPC++. So this is not necessarily in saving reports, but in basic toolkits using Jupyter Lab. I'm not
Okay,
sure what basic toolkit is. Yeah.
let me try to find the question. Um, oh, basic toolkit.
Hmm.
Um, oh, so the file. Oh, the save. Um, I actually have not used this too much, so I guess I can't really.
Yeah.
Yeah, I can't really comment on that.
Yeah.
So yeah, sorry,
Okay.
that's when I don't know.
Okay. Um, there's another one. It's asking if we have reference designs or resources that showing implementation of CNNs using oneAPI on FPGAs.
Yes, I think we do. Let me go. I
Okay.
was just in that directory. No, I guess I'm wrong. Okay, so I was thinking of the CRR. It's like,
No, CNNs. I think you
yeah,
said
so
CI.
these are the reference designs we have. So yeah, there's not a CNN one. I know we did have one of those for OpenCL, but it's not one that we ported over. So these are the ones we have today. Um, I think there's no more right now in the works. We're kind of concentrating on doing some that are more HLS based at the moment. Um, so yeah, I guess the answer is no to that one.
Okay. Someone is still typing. So while we await other questions, let me just, okay, it's there. Oh, okay. So I think it is more like a comment said, I think that's where OpenVINO will come in, converting a CNN implementation and TensorFlow, PyTorch, etc. into an implementation. Hmm.
Yes, OpenVINO does do
Yeah,
some of that.
yeah,
I'm
it
also
has
not
support.
an expert on that flow either. So, um,
Yeah,
yeah, but that's I think that's why we stopped doing the CNN examples with our like OpenCL flow and this flow is because we have the other tool that does it better. So
okay,
yeah, I think that was the background there.
yeah. So let me just ask this one that came in prior to now says how much deeper C++ is necessary to know before starting to write programs for FPGAs.
Okay, so that one, let me actually, I have a different slide deck up just in case we had some more. Oh, and I just clicked the wrong tool. There's socks. I was. Okay, so yeah, this my toolbar not working right is really driving me crazy. Okay, so this is the actually the workshop slide. So I just had these open in case we had other questions that these slides might answer. So that one I can actually reference here. Um, so to know how much DPC++ do you need to know? So this right here is actually a little program that is enough to kick off a kernel on the FPGA. So really very little do you need to know to start working with FPGA. So it's up to you, how deeply you want to dig into DPC++ before you start working with the FPGA kernels themselves. So DPC++ is scoped. I won't go into it real deep here, but just enough for you to know that all of this is on the host. And then when you get to the kernel scope here, this is the kernel scope. So after you dispatch the kernel, calling a dispatch call right here, and then all of this within the curly braces is what's running on the FPGA. And when you start diving into programming for FPGAs, this is where you actually spend most of your time, is whatever's within what's actually going to be run on the FPGA. So all of this host stuff, if you don't want to learn too much but just enough of how to encapsulate something in a buffer and then hand it off as an accessor and set up a queue, that's basically enough to get stuff kicked off on the FPGA. So don't be intimidated if you don't know a lot of C++. You don't need to know a whole lot to get started.
All right. We are just about entering the last 5 minutes of today's session, so please feel free to unmute yourself and ask questions or drop your questions in the chat window. We still have a couple of others we have before. So here is asking, there is a lot of reading material for oneAPI. So what are the most essential documents to go through?
Oh, okay. Yeah, so the two that I called out in the slides are really the two that I would go to. So let me, I was prepared for this question because it's one that came in on the form. So the this programming guide, the Intel oneAPI programming guide, this is a generic programming guide for all of the oneAPI devices that are supported. So you don't need to read all of this, but the essential chapter or section that you'll want to read is this FPGA flow, and then that goes into the flow that we briefly talked about, that you want to, compile for emulation, and then compile for an optimization report, and then finally compile for something that actually runs on the board. So all of that is explained here, along with the commands that you would want to use, and then the optimization guide. And this is all of the different techniques for optimizing for FPGA. So if you want to dig into FPGAs deeply, this is where you'll want to spend most of your time, along with the tutorials at the GitHub. So read through this, and as you're reading through this and you encounter a technique, work the tutorial that's at the GitHub, and that will give you a great education.
Okay. Oh, someone is asking, so is OpenCL better to implement CNN than oneAPI?
So actually, even they would be about the same, or actually almost exactly the same. What I was making reference to was we had a different a tool that implements CNN, so we don't encourage using OpenCL or oneAPI for CNNs as much now, because we have that different tool called OpenVino, which I think now we're encouraging the use of Core DLA, which is the same kind of tool, instead of either of those ways of doing it. So,
Okay. So we have about 2 minutes left. I'll just take this one question and then we should wrap it up. I said, it's asking, there are many tutorials at the GitHub. So how do I know what order to go in?
okay, let me show y'all that. Okay, so we have there's a lot here. So we have I thought I had this up. Okay, so first let me show you where what I'm about to show you came from. So this is our add-on website. So if this is we just gather everything about oneAPI and FPGAs here. So if you just search for Intel FPGA add-on, this is going to be the first thing that pops up in Google. And here you will find like videos and training and reference design, documentation, and a link to the GitHub. And one of the things on here is a code samples navigation guide. So if we click on that, okay, and this is a write-up that tells you exactly that, like how to go through those examples. So um, it says, getting started, a pop open the optimization guide, and work the FPGA compile and the fast recompile tutorials. And then the next here is after you've worked those and read chapter 1 of the optimization guide, then you're ready to work with explicit data movement, which tells you about buffers, printfs, pipes, kernel arg restrict, etc. And then on to some of the more complicated examples. So this is a great guide to tell you what to do step by step as you continue in your learning. Okay, so it sounds like I guess it's time. We're actually going to go a little bit
Time
over.
now.
So let me go ahead and wrap this up. Okay. So thank you everyone for attending. Thank you for all the participation and questions. That was awesome. We love feedback, so I'm going to post uh, a link to a survey in just a second in the chat. And we love feedback. It's also going to ask you like what else you would like to see as an Ask the Expert. We love that feedback too. We're always looking for ideas. And you'll also receive an email with links in about a day or two, maybe 3 or 4, but very soon. And that will have the link to the same survey and a link to the recording of this session. Okay, I'm going to go ahead and drop that link in the chat while I'm thinking about it. I have it in a notebook, not that notebook. Okay, this is my survey link. Maybe I should have given this to you. So anyway,
Yeah.
okay, there's the survey link. Okay, so I just dropped that in. Thank you for filling that out if you can. I'm going to leave this up here for just a minute. The legal disclaimers, I won't read through them, but just so that we'll have them in the recording. Okay, and flash this real fast. Okay, and thank you all for attending, and we're going to end this meeting in 60 seconds.
Thank you, everyone.